As far as I can tell, U substitution is the only calculus technique that you have to know from integral calculus on the AP Physics exam. I don't really know why it's called U substitution, other than we use the letter U to make a substitution, but it seems to be called U substitution universally in calculus. Maybe it's a joke that I'm not aware. U sub is its abbreviation, and maybe it's some kind of play on underwater boats or submarines or something. I have no idea. Here's how it goes. The idea behind U substitution is that you try to turn a new integral into an integral that you already know. For instance, in this example, we know the integral of cosine x dx happens to be sine x plus c. We already know that. But let's say we have the integral of cosine of 3x plus 1 dx. So we don't, well, actually, you might be able to guess what the integral of that is, but here's the apparatus for figuring out what the integral of cosine of 3x plus 1. What we're going to do is we're going to make a substitution for this 3x plus 1, just so it looks like this integral that we already know the answer to. So that means we're going to say u equals 3x plus 1, and the only reason why we're going to say u equals 3 plus 1 is because u is traditionally the letter we do u sub with. And notice, if I put u equals 3 plus 1, then and make the substitution, instead of 3x plus 1, I just write u in. Notice that it starts to look like this integral that I already know. And that's the major point of U substitution. What you're always going to try to do is you're going to make a substitution of U equals something in your given integral so that the given integral resembles an integral that you already know. And that's the whole point of U substitution. You try to turn an unknown integral into an integral that you already know the answer to. Now, there's a little problem with this U substitution method so far, is that when I do the substitution of u equals 3x plus 1, I get integral of cosine u dx. And if you remember stuff from before, remember this part was f of x, and it's going to be the height of a rectangle, and this part is dx, and it's going to be the width of a rectangle. And what this integral notation says is we break up the shape of the graph, cosine u, into a bunch of vertical rectangles whose width is dx and its height is cosine, and we add them up and find the area of all the rectangles, and that's how we take an integral. So this dx actually has to match up with the function of cosine, so I'm not quite ready to take the integral so far. So this I have to change this dx to match up with this u. So the next step in U substitution is changing this dx into a du, and here's how you do it. You start with this u equals 3x plus 1, and then you take the derivative in x. So you take du dx equals the derivative of 3x plus 1. The derivative of 3x is 3. The derivative of the constant 1 is 0, so du dx just equals 3. Now the next thing I'm going to do is pull one of Leibniz's famous jokes, and this is actually, I believe, this is actually Leibniz being funny. Once you have du dx equals 3, then what you do is you just solve that for dx. So you multiply both sides of the equation by dx, and that's going to cancel out the dx on this side, giving you dx equals, actually giving you du equals 3dx, and then you just divide both sides by 3. So 1/3 du equals dx. Now, and then we could make this substitution, 1/3 du is equal to dx in for this dx. So this cosine u dx becomes cosine u times 1/3 du, because we have previously found out that dx is in fact equal to 1/3 du. And since 1/3 is just a constant, we can factor out in front of the integral, and finally we have the integral of cosine du, cosine u du, and notice integral of cosine u du exactly matches an integral that we already know, namely integral of cosine u du must be sine of u plus c, and because of u substitution we know we have a 1/3 out in front of it. So for the answer we get the integral of 1/3 cosine u du must be 1/3 sine of u plus c, and then we're going to go ahead and distribute the 1/3. So I'm going to get 1/3 of sine of u, and then I'm going to get 1/3 of c, but remember it's integral calculus, 1/3 of c is just c. So I really should be writing a 1/3 c, but since c can be any constant, 1/3 c is also c. The only thing left to do now is to go back, and now that I know the integral of cosine u du is 1/3 sine of u, all I have to do now is put back my original u in for this sine of u. So the final answer is 1/3 sine of 3x plus 1 plus c. And notice I can check this by taking the derivative of this. The derivative of sine of 3x plus 1 is cosine of 3x plus 1, and then I have to apply the chain rule, so I have to multiply it by the derivative of 3x plus 1, which is 3, which cancels out this 1/3, so I do in fact get the derivative of this is in fact cosine of 3x plus 1. And that's the basic idea of what's behind u substitution. Basically, all that you do is you set u equal to something in your given integral so that it looks like an integral that you know. But the problem is, then you have a difference of variables, like here I have a u, and here I have a dx, and they have to match up. And so what you do is whatever you set this u equals 3x plus 1, you take the derivative of that, and then you solve the derivative for dx, and you make the substitution. Okay? And then it just works like you turn it into an integral that you know, you take the integral, and then you put back whatever u was originally equal to, and that's all there is to u substitution. Now I said there was a joke in here. Notice that this is the standard way to say the derivative of 3x plus 1, du dx, and specifically the x derivative. But notice that the du dx means take the derivative, and then here's Leibniz's joke. What you can do with his notation, this symbol du dx that meant take the derivative, well, then we treat it as du divided by dx, and then we do algebra on this little derivative sign, and that's kind of a joke, because remember du dx says take the derivative. It's not necessarily du divided by dx, except in Leibniz's original joke from differential calculus that this is the tiny amount, the differentially small piece of u divided by a differentially small piece of x, and that was the slope of a point, part of a point on the graph. And then we're using that idea and we're doing algebra on differentially small pieces of u and x, and then we're substituting them back in and getting an actual calculus result. So it's funny. Integral calculus is just as funny as differential calculus.